7. So what's the probability of omega without f? It's 1 minus the probability of f. So this is 1 minus 0.6, 3.4. So what is the probability of omega without E union F? And that's the probabilities. This is 1 minus the probability of E union F. So we found this probability of the union is 0.9. That one. If they wanted to find the probability of omega without, make it E, say E without omega without F. No, no, no. I want E intersect with this. So it'll be E intersected with this set omega without F. So you can rewrite this set. You take E, you want to intersect it with this set omega without F. So if you take omega, you throw out F, and then you intersect with E. That's the same as the stuff that's in E, but it's not in F. So this set has to, you're intersecting with E, so you take everything in E, and it has to be intersected with all the stuff that's not in F. So it's just E without F. So we got that picture like it in the last problem, but this is just E without F.
It's not 1 minus E without F?
What?
It's not 1 minus E without F?
For the probability, like this wouldn't be 1 minus E without F.
Yeah.
No, so.
Well, I mean, you just did this exact same equation the last one.
And this one here?
No, the one you're doing right now.
Yeah, this one?
Yeah, I mean, before you erased everything and started over, you did probability of E without intersection, omega without F, and you did P minus P without F. All right.
Yeah, so if you want the probability of this one, it'd be the probability of E. So you're saying probability of E minus probability of this intersection.
Yeah.
Yeah, that's right. So then this probability of E is 1.3. And then what's the probability of the intersection? 0. Do you guys have any questions on this? So let me tell you about this egalitarian probability function. Do you guys have any questions? So we're going to call this the egalitarian probability function. So we can define a probability function on sample space omega by this. So a probability function is this function, some function that takes every subset of the sample space and assigns to each subset some number between 0 and 1, so that all these numbers add up to 1. So you can define a probability function like this. You can just say, what's the probability of some event E? So just give me some event E. Then what I'll do is I'll just count up all the objects in E. So I'll find the cardinality of E, and I'll divide that by the cardinality of the sample space. So if you just want, so in particular, for each individual outcome, so take just one outcome in omega, you'll have that the probability of this outcome is 1 over the cardinality of omega. So, for example, let's say that you roll a die. Okay. So I want to find the probability that it is odd, and I want to find the probability that it is 4. Okay. So here you roll a die, and I want you to find the probability that the number is odd. So what's the sample space for this experiment? Can you guys identify the sample space? So I roll a die, right? So what are the possible outcomes we get? What? 1 through 6. So this is the sample space instead of all the outcomes you could possibly get. So if I want to look at this event where the number is odd, so let's let E be that event. So if E is the event that the number is odd, then what is set E going to be? 5. Okay, so if I want the probability of E, so it'll be this number of objects in E divided by the number of objects in omega. So how many objects are in E? 3. And then how many objects are in omega? 3. So now if I want to find the probability that the number is actually 4. So if I let if I'm looking at this event that the number is 4, then what's this? I want F to be that event that the number is 4, then what should F be? 4. So what's the probability of F going to be?
absolute value of f, are they all positive?
No, so when you say, when I put these bars on F, it just means the number of objects in F. So this F is a set, so, I mean, so when you put absolute value bars around a set, it just means the number of objects in the set. So I guess I could say this. So, this egalitarian probability function, so the egalitarian probability function is sometimes called the uniform probability function. And when you use this probability function, then all outcomes are equally likely. So if you use this probability function, then every single individual outcome will have the same probability. Right? So here, if we found the probability that the number would be 4, and that was just 1 over 6. So if you wanted the probability that the number would be 2, then the probability would be 1 over 6 also. So if you use this probability function, then the probability of every single individual outcome will be the same. Right? So these outcomes would be equally likely because they have the same probabilities. Right? So you should understand that you can have different probability functions on a sample space, right? So earlier we had examples where you had probability functions where, like I did those examples with, where we had capital omega had like little omega 1, little omega 2, little omega 3, and so on. And then those individual outcomes had different probabilities. So you can have a probability function that's not this egalitarian probability function. Okay. But if someone just asks you for the probability of something, right? Like in this problem, I didn't specify what the probability function was. So if they don't specify what the probability function is, by default you should go with this egalitarian probability function. Okay. So if you don't have any information about the experiment at all, then just by default you go with this probability function. Okay. So this egalitarian probability function is the default. It's the default probability function. Unless you have some kind of, experience, some prior experience in knowing what the outcome of an experiment might be. So use the egalitarian probability function whenever you don't know anything about the experiment, right? You don't have any experience